recording, right?
Yes, sir.
Otherwise, my voice is heard.
This is for recording on YouTube.
On YouTube
Yes,
also.
Yes, sir.
Thank you. So this is lecture 8.
Sir, just a minute.
Oh.
I will.
Is it okay?
Okay, sir.
All right. Are there any questions? Are there any questions? Yeah.
Are there any questions? Yeah.
Please go ahead and ask the question.
Please go ahead and ask the question.
No, you only repeat. Echo. Yeah. Hello. Can you hear me now?
Yes.
Please ask questions if you have on the quantum field theory, which I gave 1 hour lecture on quantum field theory. You can ask questions now. So with that 1 hour introduction, if you go to any elementary quantum field theory book, you might be induced to read it. Not only that, it will be now useful for the subsequent part of my lectures, which needs quantum field theory, especially the weak interaction theory. Okay.
The density of the material covered is very high.
Uh,
Last 1 hour.
yeah, because 1 or 2 semester course in quantum field theory I have compressed into 1 hour. Naturally, the density is very high. You just go over it. I mean, the lecture is there. I hope you can see it in the YouTube or something, and then go over it again and again. And any question you can always shoot me by email, or you can ask me when I come here. That is the only way to learn. You have to ask questions. And I find very few questions are being asked. So ask questions, then I will go over it again and explain it further, and that is the only way to learn. Ideally, quantum field theory course should be done first and then the elementary particle physics, because without quantum field theory there is no elementary particle physics. Otherwise, elementary particle physics will be only qualitative, as we have done so far. Certain amount of elementary particle physics can be learned, but that will be very qualitative. You cannot do any calculation, and in order to understand it deeply, you need quantum field theory. That is the message I want to emphasize again and again. Okay, so let us go to weak interaction. You will see that any knowledge of quantum field theory which you have picked up now will be useful in understanding. Even then, I am not going into very great details of any calculation or anything. Even then, the language. So just to keep your mind free, imagine things and make jumps. Otherwise, you cannot go further. You will get stuck in a corner, and that is not good. You have to keep your mind elastic. That is the only way to learn fast. And then you can come back and learn it at your leisure also. to consolidate what you have learned. But in the beginning, when you hear something which looks very, very different, you have to keep your mind elastic. Okay. Whatever I am going to say about weak interactions is contained in a review which I wrote called Fermi and the Theory of Weak Interactions.
Hi sir, there's a question from YouTube.
Pardon me?
There's a question from YouTube.
Yeah, please go ahead.
Shreya Chaudhary asks,
Yeah,
please explain neutrino in a simple way.
please explain.
Neutrinos.
Neutrinos I am coming to. I will explain neutrinos, yes. Neutrinos we introduced almost in the very first lecture, and it came as decay products of many particles, and now in weak interaction theory it plays a very important role. So I will come to weak neutrinos. You will get the explanation. In fact, if there is time, I will go into the present status of neutrino physics, namely neutrino oscillations, the discovery of neutrino mass, all that I will come to later. But right now, weak interactions in which already neutrinos will come. There is no weak interaction without neutrinos. Fermi and the theory of weak interactions. By myself. It is there in the archive. 1403. So I wrote it in 2014, I think, 2014 March. This was the original symbols. 33909. Physics, history, PH. That is the full reference. Please go to this. It will contain all the things which I am going to talk about. We start with Fermi. Enrico Fermi in 1934 constructed almost the complete theory of weak interactions. In 1934, it was a very successful theory and it held the field until it was replaced by Standard Model. Standard Model incorporated Fermi's theory as a major component. That happened in 1972. I will describe the whole story. Then we will take up Standard Model for a fuller discussion after this. So I always follow the historical route, as you would have seen. I will divide the history into two parts: pre-Standard Model and post-Standard Model. That is post-72, pre-72, 34 to 72, and 72 to now, basically. Early history. Up to 72. Becquerel discovered radioactivity in 1896 or 1897, I don't remember. And then many people, Rutherford, Curie, right? Curie, Rutherford. Rutherford in particular found that the radioactivity involves three kinds of phenomena: emission of alpha, beta, and gamma. This is after 1910. Alpha he identified as the nuclei of the helium helium atom, nuclei of the helium atom, and betas are nothing but electrons. That was proved. and gammas are nothing but photons, but very high energy photons. Very high energy photons are called gamma, and then comes X-rays, which are a little lower energy, and then all the other forms of photon coming down to visible light and even microwaves. Now, but the real understanding of, we are going to talk about this beta ray emission, that is weak interaction, and the real understanding of that came only after Fermi. And what happened was, when they studied this alpha, beta, gamma rays, Rutherford thing, for the beta ray electrons, when they measured its energies, energy of the electron, number of events, they found the energies were distributed from 0 energy up to some low energy. That energy is the Q value of the reaction, namely the, the energy of the initial nuclear state minus the final nuclear state minus the mass of the electron, and that you plot, and this is called the Q value. Q value is the energy of the energy, total energy available for the event. But since the decay resulted in beta rays, everybody would have thought that the beta electrons, the electrons would have come out with this energy. It should have been a delta function. That's what happened for alpha particle. Alpha particles from every decay comes with a unique energy, the energy difference between the initial nuclear state minus final nuclear state. And an excited nuclear state emits photons of unique energy. But electrons were continuously distributed in energy. Continuously distributed. Continuous energy. This was a big puzzle, and some people like Bohr even were prepared to give up energy conservation, saying that in fundamental events maybe energy is not conserved. Energy conservation may be a statistical phenomenon for large objects. But Pauli, Wolfgang Pauli, the same man was responsible for the Pauli exclusion principle, I think around 1932. My years are always uncertain by about plus or minus 1 or 2. He suggested that maybe part of this energy is taken away by an unseen particle, and so energy is conserved. Energy is being shared between electron and neutrino. That is why electrons come with with the continuous spectrum. That was Pauli's suggestion. I do not know how seriously Pauli himself took this suggestion, because Pauli did not publish it. He wrote it as a single paragraph to some conference organizers, which he did not attend. But the person who took it seriously was Fermi. Because he constructed the whole theory of weak interaction on the basis of the emission of the neutrino. What he did was to draw the analogy with electromagnetism. Electromagnetism is nothing but this, I already mentioned. He drew the analogy with this. Here photon is created. He said instead of photon, now two particles are created. Let us consider for definiteness a neutron beta decay. Neutron goes to proton and emits an electron and a neutrino simultaneously. Two particles are created. Particle created, that is very important. Remember in the morning I talked about particle creation, all field operators become particle creation operators. That is how quantum field theory is able to take care of particle creation or annihilation. Photon creation and absorption, that is quantum electrodynamics, that was already initiated by Dirac again in the year 1927, just 4 years after the birth of quantum mechanics itself. So he was the creator of quantum electrodynamics, although it took many more years to come to that renormalizable quantum field theory. in the hands of Schwinger, Tomonaga, Feynman, and Lysen, but that was the beginning. So quantum field theory, Dirac constructed it, and Fermi within 5 or 6 years managed to use it in a different context for weak interaction, where it is not just photon quantum of the radiation, but a material particle electron and neutrino were created. And Fermi wrote this article and sent to Nature, the famous British journal, which is used even now by people. It is a very prestigious journal. Nature editor refused to publish it, saying that what is this quantum field theory, because he did not many people did not understand quantum field theory at that time. It's only 5 or 6 years after its creation by Dirac. And what is this neutrino? It's all speculation, and nobody is interested in it, so they did not publish it. So Fermi finally published it in Novecento, an Italian journal, but he managed to publish one version of that in the German Zeitschrift also. So this is an important historical remark about Nature. Nature refused to publish Fermi's article. Anyway, so let us, that is the analogy. Electromagnetism, and this is weak interaction. Fermi's weak interaction theory. So let us write it down in terms of formulae. LE I already wrote down in the morning. An electromagnetic current. Hello? Is there a question? Is it all right? Electromagnetic current. The electric charge of the charged particle, namely electric charge of the neutron. This is the electromagnetic current with a 4-vector notation, and EMU. Remember, morning I wrote it as E into psi bar gamma mu psi. That is the electromagnetic current with the Dirac matrix there, which makes it into a vector. This is the vector electromagnetic current. Gamma 0, if you put, it is the charge density. If you put gamma 1, gamma 2, gamma 3, they are the 3 components of the current vector. So current charge density and current charge and current density are elevated into a 4-vector, again using 4-vector notation, into mu. So that is LE, which describes this, because I already said this can destroy the original electron and this can create a new electron with a different momentum. So what is Fermi's interaction? In exact analogy, first of all, a coupling constant, which is called the Fermi coupling constant now. He was the first one to introduce it, whose value, by comparing with nuclear decays, he could estimate the value also, and that is 10 power minus 5 over mp squared. Of course, H cross and C, etc., have to be put to make it agree with the common dimensions, but it is dimension is inverse of mass squared, whereas the electric charge is in this H cross and C equal to 1 dimension. You remember the very first lecture, H cross and C you don't have to put, the E squared over H cross C is simply E squared, H cross and C are 1, and this is 1 over 137, just a pure number. Whereas this requires this 10 power minus 5 attests to the word weak, that is why it is called weak. Now what is this? Here neutron has to be destroyed and proton has to be destroyed. Again use the same notation. So let me now use the particle itself to denote either the wave function in the unquantized version or in the quantized version. This is the proton field operator. Proton also in this approximation, proton is of course a fermion like electron, so it's again described by the Dirac wave function. P bar gamma mu n, neutron is destroyed, proton is created, and then we have to create electron and neutrino. You have to be careful about neutrino, antineutrino, and so on, but I will not be careful right now. Electron is created by the, this is the psi, what I called the psi, the Dirac wave function or Dirac field, but now I use E itself. So because hereafter many particles will come, so the psi is unnecessary. You use the particle symbol itself to denote its field, quantized field. So E bar gamma mu neutrino. It's either neutrino created, neutrino destroyed or neutrino created. You have to take care of particle, antiparticle and so on, but right now I will not be that careful. There is some neutrino or antineutrino, some unseen particle. Okay, that is how neutrino comes first into physics. So what does this describe? I think I have made some mistake. E bar plus its Hermitian conjugate, that will denote n bar gamma mu p into nu bar gamma mu electron field. Okay, that is Fermi's interaction, which is in exact analogy with this. Instead of photon field, actually this is called the 4 Fermion interaction. That is called because there are 4 Fermi. 4 fermionic lines meet at a point. So here the coupling constant is E, here the coupling constant is Gf, Fermi constant. So you can see that this will destroy a neutron and create a proton. Correspondingly, electron is created and neutrino or antineutrino. Whereas this will be, I think, proton will be destroyed, neutron will be created, and again positron here. This is electron plus neutrino or antineutrino. This is neutrino, I think. This is antineutrino actually. I mean, the notation is electron is considered a particle, positron is considered an antiparticle. So if electron is coming, an antineutrino has to come. If positron, the antiparticle to electron comes, then the particle neutrino has to come. This is neutron beta decay, this is proton beta decay. You know, proton does not decay, otherwise it would not be existing, because proton mass is smaller than neutron. But inside the nucleus, proton also can decay. Because inside the nucleus, we have to take care of the kinematics by looking at the whole nuclear state, because of the binding energy and so on. This the state with the neutron has reduced energy, and so many nuclei decay by the proton inside the nucleus decaying, emitting positron emission. So when I say beta decay there, it's both beta, most of them are beta minus, I think, but there are many positron emitters also. Okay, so that was Fermi's theory. This interaction, which Fermi wrote down 1934, stood the ground up to 1972 until it was replaced by Standard Model. Many developments came on the way, and Fermi's theory successfully could incorporate all those. So I am going to describe some of those now. One of the most important things which happened in weak interaction physics is the so-called parity revolution, discovery of parity violation, namely discovery of an asymmetry between left-handed coordinate system and right-handed coordinate system. Until then, all the laws, whether it is Newton's law or Maxwell's law, were symmetrical between left and right. In other words, if you have a motion picture taken of any phenomenon and you run it backwards, that also is a possible motion, although it may look very odd. Ball falling, if you take a picture and run it backwards, the ball will go up. That's also a possible motion. If you throw it from here, it will go up. Of course, many of these phenomena will violate the second law of thermodynamics, but that is a bigger thing. I will not talk about it. Thermodynamics is not invariant. No, I am not talking about time reversal. Sorry, please forget the few words which I made just now. So every phenomenon, if you look at it in a mirror, that's also a possible physical phenomenon. It does not violate anything. So both a physical phenomenon happening and its mirror reflection are possible. Both are physically possible, they are allowed. So this is called parity symmetry or left-right symmetry. All the phenomena were like that. But in weak interaction, this symmetry was proved to be violated. That is the story I am going to describe briefly. It's called parity violation. Parity itself is the transformation of any vector like x goes to minus x. Maybe all the three components may not be reversed, one component will be reversed. In a mirror, only one component is reversed, that is enough. If two components of a vector are reversed, that is equivalent to a rotation, that is not parity reflection, that is not reflection. Parity, parity is nothing but invariance under reflection, mirror reflection. Under this, if you change x to minus x everywhere in your equations, are the equations still valid? Are the equations remaining valid? If it is, then it is called parity invariance or left-right symmetric invariance. And I will say a little bit about it. I cannot say too much about it right now. The the revolution came like this. There was a puzzle called the tau theta puzzle in particle physics. In the 50s. R.H. Dalitz, Richard Dalitz, he was my professor for PhD in Chicago and Oxford. Actually, it was he who made the major contribution here. What he did was, see, look at the K-mesons which we already know. Go back to our earlier lectures. K-meson decays, there are many modes, pi plus pi 0. This is called the theta mode. And it decays into 3 pi's also, pi plus, pi minus, pi plus also. This is called the tau mode. Actually, they were considered different particles because if you look at the parity of this, remember pi, I wrote 0 minus, spin 0, parity minus. I used the word parity already. Every particle has an intrinsic parity like intrinsic spin. That is, when you reflect the coordinate system, when you consider this, the wave function of that particle should be given an extra minus sign. Wave function will depend on x, so x will go to minus x, and that will introduce some signs. Where remember minus 1 power L for all the Legendre polynomials in hydrogen atom, you would have learnt it. In addition, we have to put another extra minus sign because they are negative parity particles. But there are two of them, and this reflection symmetry is multiplicative symmetry. If two of them are other minus 1 into minus 1, so it is plus 1. And the spin of this is 0, so the angular momentum of this is 0, angular momentum of this is 0. So it's not a Legendre polynomial, it is just 1. So it does not change sign. So the parity of this system is plus. So the parity of this therefore is plus. Whereas if you look at this, is more complicated. 3 of them, they give you minus 1. There are angular momenta, and that is where Dalitz made the contribution. He showed that the relative angular momentum also is 0 for all of them. That's through what is called the Dalitz plot, a phase space plot. We call it. It's called nowadays Dalitz plot, which plays a very important role in much of experimental physics. And using that, he showed that the relative orbital angular momentum between these particles also is 0. So, and spin is 0. But intrinsic parity is minus 1 power 3. So it is minus. Intrinsic parity is plus intrinsic parity, and final state minus intrinsic parity. So at that time, parity was considered to be considered to be conserved. Left-right symmetry was considered to be a symmetry of all equations of physics. So they thought that these are two different particles. But when they looked at the mass of the total energy and momentum, and hence mass can be determined, so-called invariant mass. Here also mass was exactly the same. So this was a puzzle. How can two particles with different parities have exactly the same mass? Then T.D. Lee, so Dalitz analysis was in the year 54 to 55, around that time. T.D. Lee and C.N. Yang, I think that was 1955, they suggested that maybe parity is not conserved. These are weak decays, remember, these are weak decays. Strangeness is not conserved, remember, so these are weak decays. That we already know. And perhaps they thought that maybe in weak interaction parity is not conserved. That was a mere suggestion, but they analyzed all the experiments done up to that time in weak decays, namely beta decays only, and found that there was nobody who checked whether parity is conserved in those decays. So they raised a question. They left it like that. Is parity conserved? That was the title of their paper, I think. And the person who did the experiment was C.S. Wu. All the three were in Brookhaven National Laboratory and Columbia University, I think, Columbia University. So they said parity is perhaps not conserved. Only experiment can answer the question, and the experiment was done by T.D. Lee, I mean C.S. Wu, 1956, around the same year. I think immediately they did the experiment. What they did was, they aligned, they oriented all the nuclei by a magnetic field so that all the spins were pointing in one direction. I think they chose cobalt nucleus with spin up, cobalt 60. How did they align it? By a magnetic field. I don't know whether magnetic field was this way or that way, but let me indicate magnetic field by the current carrying coil. Okay, this is the cobalt nucleus. So they observed the decays. They found that more beta particles came this way and less came this way. Now this is definitely parity violation. Why? Because if you look at this is the right-handed coordinate system x, y, z. If you rotate the x to y, a screw will go this direction, right? If you rotate like this, screws will go. So this is called the right-handed coordinate system. And in a mirror, if you put a mirror here, how will it look like? Z here, and y here, and x here. Here x and y, x to y, z, if it has to go this way, this is a left-handed screw. This is a left-handed screw, this is a right-handed screw. You can do that for this experiment also. Because of this rotation, you will find that put a mirror here. How will it go? It will go like this now. More beta particles here and less here, and you will see that in a mirror this is very different, because this will correspond to a left-handed coordinate system. I mean, think of the screw, left-handed screw and right-handed screw. This is left-handed. This is called a right-handed coordinate system, left-handed coordinate system, and so this will not be a physical process. What they observed was this. So that is proof of parity violation. Another way of looking at it is, I don't know whether I should talk about that. Think of intergalactic communication. Suppose you want to communicate to your friend in some distant galaxy what is that he has to use for this experiment, yeah, right-handed coordinate system. You can use this physical phenomenon, use currents going in this direction and currents going in this direction, and then if more beta particles come in this direction as measured by this screw, more up and down are distinguished by the direction of this current carrying coil or the direction of B. Okay, either way you can communicate to him that the direction in which the currents go and the more beta particles coming, that defines the right-handed coordinate system. You can say it in words through radio waves, and he will know what is a right-hand, because you cannot use right-handed or left-handed screws, because we do not know what in that planet, what kind of screw they use, right-handed or left-handed. So you cannot use such things. Only physical laws are universal everywhere, so you can use that. But of course, you have to be careful in that. You have to make sure that he as well as his planet are all made of particles and not antiparticles. Now we know that that is true, because there is no part of the universe which is made up of only antiparticles have all disappeared. So you can use that. Because of weak interaction which violates parity, it is possible to make an intergalactic communication and inform the other fellow what a right-handed coordinate system is. So that is one way of understanding the importance of the parity violation. So this established that weak interactions violate parity. I think this is the right time to say one thing more. This is P violation. I think I can remove this now. Actually, something more has to be said here. But I think this is the right place to talk about so-called CP violation. This is parity violation. Weak interactions violate parity, and at that time it was thought that if you not only go x2 minus x, that is P, but particle, wherever particle is there, change it to antiparticle, that is called C. So apply both these operations simultaneously, then weak interaction perhaps is invariant, because this violation, parity violation was a big revolution. People like Pauli, when he heard that CSU is going to do that experiment, he said, no, I don't believe that she will succeed in proving parity violation. So many people did not believe it, but it was there experimentally. So that is why it was it is called a revolution. So they tried to satisfy themselves, saying that maybe weak interaction violates parity, but violates C also by equal amount, so CP is conserved. Namely, the theory is invariant under CP. That's what they thought. Unfortunately, experimentalists disproved this also. CP violation. That was done by Cronin and Fitch. Pure experimental discovery. Parity violation, at least there was some theoretical suggestion, but for this there was nothing. It was a pure experimental discovery. Again in KD case, in the year 1964, they proved that CP is conserved. Now this is very important. I don't know whether, I think I mentioned in the first lecture, how many of you remember, I do not know, that the baryon asymmetry of the universe, because the universe in the Big Bang, equal amount of particle and antiparticle would have been created, equal amount of nucleon and antinucleon, equal amount of electron and positron. But now the whole world is made up of only matter. All the antimatter disappeared, and it's possible to explain this provided a few conditions are satisfied. It was Zakharov who formulated those conditions. One of those conditions is CP has to be violated. So that's why Cronin and Fitch's discovery is very important to solve this matter-antimatter asymmetry in the universe. And so they were given Nobel Prize, I think, almost immediately. That is CP violation. I will not talk more about it, although it is a very important subject in particle physics, even now. Because we have to now incorporate that into standard model. It has been done, whether it is completely correct and so on. I will take up those questions later. Actually, neutrino physics plays a very important role in this also. But now, since I am pursuing Fermi's theory now, Fermi's theory survived even this fundamental revolution in physics. Remember, Fermi had the intuition to put a better interaction. There are many other interactions possible. since electromagnetism goes through a vector interaction, namely electromagnetic current, he chose a vector current for his weak current also. Remember, I put a gamma mu. So it was a pure vector interaction in Fermi's theory. All one had to do now, as a consequence of this discovery by C.S. Wu, yeah, these guys got Nobel Prize. Li and Yang. Again, Nobel Committee made a big mistake. They did not include C.S. Wu, who was the one who really established the parity violation. She did not get it. Li and Yang got it. But anyway, so the pure vector interaction of Fermi's theory has to be replaced by a combination of vector and axial vector. They have opposite transformation property under parity. The vector part of gamma mu, namely gamma I, goes to minus gamma I in vector, just like the position vector x goes to minus x, whereas the axial vector under parity reflection remains the same. That is why it's called axial vector. You all know what is an axial vector. The simplest example is angular momentum, magnetic field. These are all axial vectors, because remember, angular momentum, orbital angular momentum, is r cross p. So when you do a parity reflection, this also changes sign, this also changes sign. So L does not change. So L is an axial vector. Similarly, magnetic field, if you look at Maxwell's equation, it will become clear that B also is an axial vector. It is connected with this rotation. Anything connected with rotation like angular momentum is an axial vector. Okay. So we have to add this. So Fermi's interaction was vector times vector. So you put V minus A there in the first place, V minus A in the second place also. So there will be a cross term BA, which will behave differently from BV term and AA term. So both some terms change sign, sometimes don't change sign. So under parity reflection, it is not invariant. That's as simple as that. Is the explanation of the Wu's experiment. More clearly, remember the gamma mu which came there between n bar and p and so on. Let me write it down fully. E bar gamma mu. This is Fermi's interaction plus Hermitian conjugate. So replace gamma mu. This is a pure vector. This is a pure vector. This is a pure vector. So it's a scalar. We need a pseudo scalar. For that, you have to put gamma mu into gamma 1 minus gamma phi. Again, I have to introduce this Dirac matrix. Replace gamma mu here as well as here by this combination, because gamma phi gamma mu n bar p is an axial vector. Whereas gamma mu, the original form, is a vector. By adding this, this is called the B minus A interaction. This was proposed by Sudarshan and Marshak. Sudarshan and Marshak were together. Feynman, Gell-Mann, and Sakurai almost immediately and independently. This was the V minus A. The V minus A interaction was proposed by these people. Now we know that is correct, and that was done in the year 1957. But remember, Fermi himself chose this. So as soon as Wu did this, anybody could have simply added this. This is the most elegant way of changing the vector to vector and axial vector. But unfortunately, what had happened was, meanwhile, before the parity revolution came, people said instead of gamma mu, don't put gamma anything, because still it can describe the weak interaction, or put something else. So if you don't put anything, put 1, that is the scalar interaction. And then the vector interaction which Fermi chose. And then you can put a tensor. There is a way of forming tensor by multiplying 2 gamma matrices. Tensor, then the axial vector. By axial vector, I mean axial vector times axial vector, which will be a scalar, which will not violate parity. And then the so-called pseudo-scalar by putting a gamma phi. When I put gamma phi here, I should make one statement. Remember, the Dirac matrices satisfy the anti-commutation relations. They are the definitions of the gamma matrices. Any 4 matrices satisfying this equation. This G mu is again that 1 minus 1 minus 1 metric tensor. These are the 4 Dirac matrices. It turns out that if you form a product of all the gamma matrices, gamma 0, gamma 1, gamma 2, gamma 3, this gamma phi anti-commutes with all the gamma matrices. That is the important property of the gamma phi matrices. And it is this gamma phi matrix when multiplied by gamma mu becomes an anti axial vector. So that is an axial vector. So that is the B minus A theory, so called. So what I was going to say was, in between the Fermi's theory and time of Fermi's theory and the time of parity discovery during those 20 years or so, people tried all these other things. They complicated the weak interaction theory unnecessarily. So it became a mess. So they tried to determine which of them really describes the weak interaction. If they had ignored all that, put only vector, as soon as who discovered it, you could have added A and got the V minus A theory. But anyway, that is a historical fact. So during the years 47 to 55 or so, many particles were discovered, which we have described in our particle physics lecture so far. Pi mesons, K mesons, the hyperons, lambda, sigma, cascade, all these things were discovered and their weak decays were studied. All of them, most of them decayed, except for the resonances, so-called resonances. All the other particles decayed only by weak interactions. All the original non-strange as well as strange particles decayed by weak interaction. So weak interaction became a very complicated phenomenon because all the particles decayed by weak interactions. Weak interaction became, in some sense, a universal phenomenon of all particle physics. So I am coming to the years 1947 to 55. Just a little bit before the parity revolution. So many particles, mu, pi, k, lambda, sigma, cascade, all these were discovered and their weak decays were studied. And Fermi's theory was on the so the parity violation could be incorporated very elegantly into Fermi's theory. How about the decays of all these particles? Because the Fermi's original form gave you the decay of neutron into proton, but what about these? Now that was the achievement of Feynman-Gellman. Again, the same paper in which Feynman-Gellman proposed B minus A, they proposed this form. (1957). So let me call it the Lagrangian density Feynman-Gellman form. Same Fermi form, G. I don't know whether I wrote all these numbers. Yeah. Fermi coupling constant divided by some numbers have to be put. So let me explain. J plus J minus plus J minus J plus. In general, this is different. Remember, these are all operators, so you have to write this also. It is not Hermitian conjugate. Anyway, let me not bother you with those. Now, what is J plus? J plus is equal to, in this, the original Fermi form. I will not write down this gamma mu or gamma mu into 1 minus gamma phi. Whenever I write like this in weak interaction theory, please remember you have to sandwich this Dirac matrix gamma mu into gamma phi between the two fields. One field for destroying, one field for creating. In between, you have to put these matrices. I will explain what I am trying to do. J minus is just the Hermitian conjugate of this, so it will basically come as the reverse of this. I am writing nu E which comes with E and nu mu which comes with mu. That itself is an important discovery that the two neutrinos are different. Now we know that there are three neutrinos, one corresponding to tau and so on, but that is a different story. We will describe it in detail later. The important point is Feynman and Gell-Mann suggested that instead of taking only p bar n and nu bar e, you write sum all these. Remember, all these are charge increasing. That's why I write J plus is charge increasing by 1 unit. Neutron is destroyed, proton is created, increase of charge by 1 unit. Electron with negative charge is destroyed, neutrino is created, charge increases here also. So all charge increasing things are J plus, all charge decreasing. And this described all of them, the mu decay, pi decay and all that. You can write down corresponding to the strange particles, you can put all these things. So you can go on adding these terms. So this concise form describes, this is the generalized Fermi interaction, you can say, incorporates all the decays of all the elementary particles. Let me give you a pictorial representation of this, that's very useful. That J plus and J minus can be pictorially represented. Remember, J plus destroys an N and creates a P, and then we add that to destruction of an electron, negatively charged electron, and creation of a nu E. Similarly, mu and nu mu. So this is J plus, and we multiply that by J minus, which is just opposite. P n nu E electron and nu mu neon and so on. Put some dots here. More terms can be easily added. Multiply this and this. For example, take take this with this, you will get n decay. Neutron decay, or take mu here, this term mu E nu E bar, that will be mu decay. Remember, mu decay was precisely this. Mu goes to 2 neutrinos and 1 electron, or you can even think of this mu nu mu and P into n. That will be muon absorption in the nucleus and the proton getting converted into n in the process. So let me call it mu absorption in nucleus, mu absorption by proton in the nucleus, or even by hydrogen. It can be, that process also has been seen and studied. So many of these processes, there are 3 into 3 9 process, but since there are dots, so you can see all the decays could be accommodated. So that was the achievement of the Feynman-Gell-Mann form of the Fermi interaction. I will just make one remark about neutrinos, because neutrinos play a very important role in all of weak interaction physics. So we will come back to further study of neutrinos later, but for the moment let me say this. Yeah. Pauli suggested the presence of neutrino, and Fermi made a successful theory of it, and that theory was subjected to experiment on various decaying nuclei in the subsequent 2 decades, that is to 50s, and it was confirmed experimentally that it is correct. So nobody had any doubt that Fermi's theory, neutrinos exist, especially the theorists, because Fermi's theory was verified. But that was not accepted by 2 experimentalists. Kovan and Reines. They said that's not enough for science. If neutrinos are emitted along with the electrons in beta decay, we should be able to detect the neutrinos also. That's what they said, and they managed to detect it in the year 1956. Remember, that is the time after the World War when two bombs destroyed two cities in Japan, and America, Russia, and France, and so on, even UK, I think, were doing nuclear bomb tests on the surface of the Earth. Finally, it was abolished. That tests were forbidden, but they were doing it. So Kovan and Reines wanted to go near a nuclear explosion, test explosion, and detect the neutrinos, because every fission, nuclear fission, creates many radioactive nuclei, beta decays, copious production of neutrinos come. So they wanted to put a neutrino detector and detect it. Of course, for obvious reasons, they were prevented from doing so. But then they went near a nuclear reactor, the Savannah River power reactor, because every nuclear fission reactor, like our Kodangulam reactor, is a copious producer of neutrinos, or rather antineutrinos. What they produce are antineutrinos. So they went near the Savannah River reactor in USA and managed to detect the antineutrinos for the first time. That was the experimental discovery of neutrinos, or rather antineutrinos, and Reines got the Nobel Prize much later, I think in the 70s or 80s, I don't remember. Kovan missed it because he had died by that time. That is one thing. And from that time on, neutrino experiments and neutrino physics picked up, and we will talk about it later. But one thing I will mention, rather two things. How was it proved that nu mu is different from nu e? See, high energy accelerators produce proton, you accelerate them, and make the protons impingent on material. It produces pions, and pions produce mu and neutrino. Pi decay, I think I mentioned it earlier. Look at the pions and look at this. Pi plus will give you mu plus, pi minus will give you mu minus, and neutrino or antineutrino, depending on whether it is particle here or antiparticle. Now, then they simply flushed out the mu by putting a magnet or something, so that what came in the directly after that was only neutrinos, only was left in the beam. So they made these neutrinos interact with other material, and neutrino, I don't know what they did, maybe let us put proton, neutrino plus proton can give you neutron plus E plus, right? Yeah, that's possible. But they found none of these neutrinos produced positrons. Rather, their energy was sufficiently high that they produced mu plus. So these neutrinos coming associated with mu have to be denoted as nu mu, and those nu mu's are not the same as nu e. Only nu e can produce this. Okay, this is nu e, and what is coming here is nu mu, and that can produce only mu plus. That was the discovery, that nu mu is different from nu e, and that discovery was made by Schwartz was there, but I don't remember the other fellows' names. Maybe Lederman was there, but I am not sure. You can check from books. That happened around 1964, I think. So I don't know whether they got Nobel Prize for this. Lederman got Nobel Prize. I don't know whether it was for this, but for that epsilon discovery, I don't remember now. So that is the second point. Now we know that there is one more neutrino, because like electron and mu charged particle, there is a tau. Along with the tau, there is a nu tau that is also different from nu e or nu mu. So there are three neutrinos. So from tau, you get nu tau. which is different from mu different from mu. So there are 3 neutrinos. So we will study these 3 neutrinos and their oscillations among them, so why they oscillate, all that. Oh, that's all very simple phenomenon, quantum mechanical phenomenon, no field theory is needed. So we will describe that later. The third important thing I want to mention is the KGF experiment, Kolar Goldfield mines, which are on the way to Bangalore, I think. So in 1965, the atmospheric neutrinos, they are called atmospheric neutrinos, were detected by the team working in the Kolar Goldfield mines in 1965. This was an important thing. Atmospheric neutrinos. What are atmospheric neutrinos? Atmospheric neutrinos are, you can call them cosmic ray produced neutrinos. Cosmic rays are very high energy protons coming and impingent on the atmosphere everywhere, and this high energy proton impingent on nitrogen or oxygen nucleus generates many particles, and many of them are pions and so on, and pions and muons and so on. Pions decay into mu, as we already know. Remember the original discovery of pi mu chain and so on. So pi decays into mu, mu also decays. All of them decay into neutrinos. And if you go deep down into the mine, Kolar Goldfield mines are about 3 kilometer depth. At that depth, all the other particles get filtered by the rock above, 2 or 3 kilometers of rock, and your detector becomes sensitive to neutrinos. If the other particles are coming like mu, mu's are penetrating particles, as Baba found, and the original experiment was to check the flux of the muons as a function of the depth. That is why Baba sent these people to the Kolar Goldfield mines. But they had reached a depth of 3 kilometers where the detector was silent. Then they realized that they have reached a depth at which the very weakly interacting neutrinos could be detected. They went ahead and detected. That was the first detection of atmospheric neutrinos in this country. And it is these atmospheric neutrinos which are going to be researched on by the INO, India Basin Neutrino Observatory. But that's a different story. How much of it I will tell, I do not know. Maybe one lecture I can give on all those later, the later part of the lectures. Okay, I think I will stop here now. We have come up to, we have done the pre-1972 version of the Fermi, Feynman-Gilman theory. So now we can go to the weak interaction after 1972. And in that, I will start introducing the standard model version of Fermi's theory. But that will not be a full story of standard model, which we will take up later. Okay, so that is the aim. So if you have any questions, you can ask me now. Otherwise, lecture-wise, I am stopping here.
Actually, Balasubramaniam shared a link.
Pardon me?
Balasubramaniam shared a link.
Balasundaram?
Wherein, in honor of CS Wu, US government has released a stamp, postal stamp. This month.
Oh, that's very good. When was that? At that time, is it?
This month, February 2021. There is an article in Science.
Oh, I see. That's very good. That's very good. That's very good.
Yeah, so Balasubramaniam shared that link.
Very good. Very good. So please send it to me also. I can also have a look at it.
Yeah.
Because CSU was missed by the Nobel Committee, which was very unfair. Of course, her experiment was very simple, but nevertheless, she did it. I think within a few months after Li and Yang suggested that parity may not be considered parity may be violated, she managed to do it. That was a very important milestone in weak interaction physics. Okay. Any other question or comment?
Yeah, I think we will meet next week.
Pardon me? Yeah, we will.
There are no questions. we will meet.
Yeah, if there is no further question right now, you can ask me later also. So we will meet next week.